Greetings, everyone. This is Stephen Feuerstein. I'm an architect at Oracle Corporation, and I'm here to talk to you about 10 other top tips for improving PL SQL performance. So this is the third in my series of performance-related webcasts that have been co-sponsored by ODTUG and Oracle Technology Network. Thanks for joining me, and thanks to ODTUG and OTN for hosting. If you'd like to get more information from me about PL SQL, feel free to send me an email. But of course, visit my blog, follow my Twitter handle, and then you can find out about all sorts of ongoing PL SQL related topics.
Yeah, I was looking there.
So, how to benefit most from this training? Obviously, we have an hour. I have a lot to cover. You're soon about to see the agenda. That's a lot of stuff. And you really can't internalize everything about these features by listening to a one-hour webcast. So what I do during the class is make sure that you have opportunities to ask questions, and we'll do that at the end of the talk here via chat. But mainly what you want to do is focus on concepts and principles, the basic ideas behind the drivers behind these features, where to use them. And then afterwards, you can download and use my training materials. So you'll see lots of references to files, and I'll be showing you scripts during the talk. And you can download all of those from the PL SQL Learning Library, which is at oracle.com/OLL, which is the Oracle Learning Library. And then just add PL SQL. Whoops, wow, that's a pretty bad typo. Here, let's show you how dynamic I am. Let's fix that.
Well, we haven't done that.
Let's fix that typo. There we go. And back in we go. By the way, I'm hearing some background voices. I don't know if the recording is catching that, but if anybody's not muted, you might want to mute yourselves. Okay, so oracle.com/OLL PL SQL. And then you'll be able to download a demo zip file that contains all the scripts that I reference in this training and all my different trainings, including, for example, the HR schema install script that will install the standard HR demonstration tables. You can use all of my scripts, all of my PowerPoints, my training materials for your own internal applications. But please don't assume that they're production ready. In other words, you should test them and modify them to make sure they fit your needs. So the agenda for today. First of all, when and how do you optimize your code? I want to take a step back, look at the big picture to make sure that you're correctly picking the right time and approach to optimization. We'll take a look at the optimizing PL SQL compiler. Let's let Oracle do all the work for you that we can get them to do. We'll take a look at some advanced collection features, array structures in PL SQL, and how you might put them to use. Take a look at calling PL SQL functions from SQL. The NOCOPY hint, table functions, including pipeline table functions, optimizing data types, and basic SQL and PL SQL optimizations. That is a lot. In fact, it's way too much for 1 hour. So like I say, I'm going to cover it at a pretty high level, and then you can dive in from there afterwards through my books, through online resources, and my scripts. Whoa, there's something wrong with my this and that. So let's do something else. What the heck? Let's turn off the animation. It is turned off. Okay. Well, my apologies. We'll get through it somehow. I thought I'd fixed it. Okay. So let's talk about when to optimize your code. We always want our programs to run faster, but remember the 80-20 rule. Most of your code's never going to be part of a bottleneck, so don't obsess about optimizing every single line of code. In other words, you could pick up the user's guide, you could pick up my Oracle PL SQL programming book, read the section on optimization, and memorize every single little item. And then every time you write a program, apply every single potential optimization rule. But that's a waste of time. You'll optimize code that no one will ever notice the optimization results of. So here's what I suggest you do. First of all, apply key optimization features proactively, which means, first of all, writing and optimizing your SQL, then making sure you do bulk processing for multi-row SQL operations, FORALL and BULK COLLECT. Use the function result cache. These are all topics covered in the 2 previous webcasts in this series and available online from ODTUG through YouTube, PL SQL Learning Library. So you've got the big pieces in place. You haven't done anything obviously bad from a performance standpoint. The next step is to prioritize maintainability of your code. So the most important thing to look at here is writing your code so that a year from now, 5 years from now, somebody else can come and manage your code without having a nervous breakdown, being able to understand and work with that code. Otherwise, it's going to be really hard to do any further optimizations, among other things. Then, once your application is correct, it meets user requirements, then what you want to do is identify performance bottlenecks. Where is it running slowly? And to do that, you might take advantage of two different profiler packages from Oracle, DBMS Profiler and DBMS HProf. DBMS Profiler, available prior to 12c, gives you the ability to analyze the performance of each individual line of code. DBMS HProf, actually introduced in 11g, is called the hierarchical profiler, and that allows you to much more easily identify the sub-program units as a whole that are the bottlenecks. Once you identify those programs, then you can dive into applying more specialized optimization techniques as needed. So, for example, one of the topics I'm going to talk about is optimizing data types. Choosing, for example, PLS integer versus integer. The chance of a technique like that really making a difference for you is tiny unless you have a highly specialized program, and that's the sort of thing you'd identify through your bottleneck analysis. So the main thing is be aware of and take advantage of those big picture items, and then don't worry so much about optimization until you've identified the need for it. My apologies. So what can I do to optimize the following procedure? Let's take a look at an exercise. Here's a piece of code. The Pilch loop procedure takes in 3 different values, all in parameters, and obviously it's a pretty dumb program. It loops through those million iterations, or is it 10 million iterations, and calculates a summed up result, which is always the previous result plus value 1 plus value 2 divided by value 3. Now, hopefully, you've been around the world of programming long enough to say, oh my gosh, Stephen, that is a loop invariant. These values never change. They're all in parameters. So why would you calculate it over and over and over again? And that's a really good point. One of the main optimizations one might look for are loop invariants, things that are executed within the loop, but aren't the results of the expression aren't affected by the current state of the loop. And back in the old days of Oracle, prior to 10G, this could actually have caused a performance degradation. But the answer today to what can I do to optimize this procedure is really not very much of anything at all. Because in the modern world of Oracle PLSQL, as of Oracle 10G, Oracle provides you with its own optimizing compiler, and it's smart enough to say, oh, wait a minute, that's a loop invariant. Well, why would we calculate that over and over again? Let's just calculate it once, put it in a local variable which we generate automatically and transparently, invisibly, and then we'll put that local variable in the place of this expression. So that's what Oracle does for us behind the scenes. So if you're on 10G or higher, and I assume you pretty much got to be at this point, and you have your optimization level set to 2 or higher, so 2 is the default, and prior to 11G it was the most aggressive form of optimization. As long as you leave it set at the default, you don't have to worry about things like loop invariants and many other aspects of optimization of your code. Oracle will take care of it for you. And I can go into a lot more detail about these different levels and so on and so forth, but the bottom line is you should really not ever change it. At most, you might want to set it up to 3, and we'll focus on that a little bit further down the line. But in general, leaving it 2 is just perfectly fine, and it gives Oracle the freedom to automatically optimize your code. So here are some examples of automatic optimization. As I mentioned before, if Oracle sees an invariant inside the loop, it will automatically replace that with an expression. If it notices that there are similar expressions just in your code, it will do the same kind of replacement. And here's one that's really great that I love to point out. It'll automatically optimize cursor for loops to execute as if they were bulk collect. Let's take a look at the script. So this is one of the scripts on my pages. That name of that file is in my demo zip script, and you can use it yourself. You can download the demo zip. You can try it out. And in fact, with any of my performance optimization scripts, I encourage you to make sure that you've tested it in your environment on your database, and you can reproduce the behavior that I say you should get, because you shouldn't just trust me. And this is something you can run right out of your database without installing any other objects. It basically fetches 100,000 rows from the all-source data dictionary view. And it compares a few different ways of doing fetching. One is the cursor for loop. Another is an explicit row-by-row fetch. And the third uses bulk collect, fetching 100 rows at a time. Now, I'm not going to go through running all of this. I can just show you the results at the bottom. But in the code that you run, it'll automatically change the optimization level. And here's how you can do it if you wanted to set it explicitly. Here's turning it off. Here's turning it back on. And what you'll find is that if you turn off optimization, the performance of an implicit and explicit cursor for loop will be quite similar, but bulk fetch will be noticeably faster, in this case about a third of the time. But if I turn on default optimization, notice what happens. The bulk fetch and the cursor for loop run in roughly the same amount of time. Usually, actually, the bulk fetch, the explicit bulk collect, might run a little bit faster, but in general, you won't see much of a difference. So that's really nice, and it's a very advanced form of optimization, of automatic optimization in code, which is different, I think, quite different in shape and significance than the standard optimizations that you'll see from any program, any language optimizer, things like this. Oracle really sat down to the PL SQL team, sat down and thought about the different ways that they could do as much as possible to help us. And what they recognized here, and it's an important point about programming in general, is that a cursor for loop is a declarative statement. It's like an SQL statement. When you write a select statement, you're not saying how to get the data. You're saying, this is the data I want. With a cursor for loop, you're saying, I want to fetch through each row and do something. The details of open, fetch, exit, when, close. You take care of that for me, Oracle, and Oracle does. And because Oracle takes care of the implementational details for you, at the time of compilation, Oracle has the opportunity to change how it implements that cursor for loop. Now, it doesn't actually turn a cursor for loop into a bulk collect. It turns it into C code that operates with array processing. But the bottom line is that you get automatic optimization. Really nice stuff. Now, it's true that in Oracle 11g, Oracle added a new level of optimization, which is level 3. And that allows you to do inlining of local subprograms. So basically, if you've created procedures and functions inside other procedures and functions, but the normal behavior is that when that function is called or that procedure is called, there's a link to the actual code. It's a reference inside your compiled code. So there's a slight delay in the lookup of the code for the invocation. When you turn on inlining, it basically replaces all the invocations of subprograms with the body of code itself. So what that means, among other things, is that your compiled code size increases. So if I have a procedure, a sub-procedure of 1,000 lines and I call it in 10 places, then my compiled code will reflect 10 times 1,000 lines of code, 10,000 lines of additional code. But that really shouldn't matter to us very much. The main thing to be concerned about with inlining is that it could actually slow down your code overall by precluding or making impossible to apply other later optimizations. So I would say that inlining is probably something you only want to use when you've identified a really clear need. In other words, if you are recursively calling nested subprograms thousands of times, or just doing a lot of nested subprogram calls, this might help you. In general, it's an example of one of those highly specialized optimizations. To learn more about the PL SQL Optimizer, and there's a lot more to learn about, and I think it's a good exercise for you in terms of deepening your awareness of what they're doing to help us write better PL SQL code, you can check out this URL or just search on any of these titles. These first two are specifically about the optimizer, and the second two are pieces that Bryn Llewellyn and the PL SQL Product Manager wrote to help you explore and debunk myths about PL SQL performance, things that people say about PL SQL and performance that really might not be true, and helping you by giving you a performance measurement harness to do the analysis in. So good resources, check them out. Oh, yes, yes, yes. Okay, so here's another piece of code. How can I make this code run faster? So this is a package I wrote called String Tracker. To keep track of the names of variables that I was using in my program because I was generating packages and I wanted to make sure I didn't have duplicates. So basically every time that I used a string name, I would throw it into my list, my array of G names used. And then to find that if a string is in use, I would pass in that name, find out how many I've got to look for, start at the first one, and then while I haven't found a match, check to see if the name is in the array. And then go to the next one and keep doing it around and around and around until I find a match, and then I return whether or not a match was found. So this is the kind of code I could write with my array structures, and I can easily build these kinds of packages. In fact, let's take a look at the whole package. So here's my list of use names, It's a table of variable names, which is varchar2 32767. I put the string in the array, incrementally adding it to the list, just adding it sequentially to the list, and then I iterate through it to find a match. Probably doesn't run too slowly, but among other things, it's a lot of code to write. It's a lot of code to manage, to debug, et cetera, and you've got to deal with the boundary conditions in your loop. And what's really important is that this is clearly not a data-neutral algorithm. And one of the things you want to look for in optimization is writing code so that as your data patterns change, specifically as your data volumes grow larger and larger, you shouldn't see degradation of performance. But that is exactly what you would see here, because depending on where the match is in the list, or maybe it's not in the list at all, I have to go through the entire array structure. This is essentially, potentially, a full collection scan. So as the collection gets bigger and bigger, my code gets slower and slower. Now, to be quite honest, practically speaking, you're probably never going to hit a problem in performance with this code. Iterating through collections is so fast. But still, it's not the right way to go, and there are better ways to approach it. So what I wanted to introduce to you is the idea of working with associative arrays, and specifically the string-indexed versions of them. So this is not the time or the place to give you a full demonstration or a training on collections and associative arrays. But of the three types of collections in PL SQL, associative arrays is probably the most flexible to use. It's PL SQL only. You can't use it in SQL statements, though you can actually in 12.1 a little bit. And they're very fast because when you work with collections, and this is true for any collection type, you're working with PGA or Process Global Area-based memory, not SGA. The really cool thing about associative arrays is that you can index by integer or string, not just by integer. You can fill them densely or sparsely. I can fill them up sequentially, which is what I showed you here. Come on. This is an example of sequentially filling a collection. Get the count, how many are in the array now, and add 1 to it, so it puts it in 1, then 2, then 3, then 4. But you can also fill them sparsely. Essentially, you can emulate a primary key in an associative array. Now, the key thing here to keep in mind about collections, pardon me, is that not all data that you're manipulating needs to be stored in tables and manipulated by SQL. In fact, my most recent article in Oracle Magazine talks about situations where you may not want to make your data persist or pay for the cost of persistence in a database table. Sometimes we're manipulating memory entirely, manipulating data entirely in memory. The data is present during my session, and it's only valid during that session. And if you have that situation, using collections can really improve performance quite dramatically. So what I'd like to do is show how you can apply this really nice feature, string index collections, to greatly streamline your code and get better performance. So if I'm doing a full collection scan in my code, as you would when you're looking at SQL and relational tables, you would say to yourself, well, I don't want to do a full collection scan. Maybe I should add an index. Now, with PL SQL collections, you can't add an index. There's just one index per array. But what you can do is change the type of index. I'm going to go back to the code. So in my first iteration of string tracker, I have an integer array, integer indexed array, and I simply add sequentially to the list. Now, adding sequentially to a list makes sense if the order in which things are added are significant. Like if you're building a stack and you need to pop the stack, the order is quite significant. First in, last out. In this case, the order is not significant. I simply want to know if it's in there. So here's an alternative approach. Now I'm using a table of, well, now you get to look at some interesting ways in the way I write code. I like to use subtypes, which give me names for base data types, and constants to give me names over special values. So I'm saying that my use list is a table of who cares. It's a table of Booleans, but I don't care what its value is, indexed by the value string, which is the varchar2. So this is a string index collection of Booleans, but it looks like I don't care what the values are. Now, why would that be? Well, think about indexed organized tables. You might have an index that contains all the information you need to resolve your query, so we never actually look at the table itself. That's what we're looking at here. So now if I look at, you know what, this is the more complicated version. Let's look at string tracker 1. Same basic idea. Table of who cares, indexed by variable name. And now when I mark it as used, rather than adding sequentially to my array by count plus 1, I use the string as the index value. It's a string index collection. So I say that the string, the index is the variable name. The value that I'm putting into the collection doesn't matter a bit. It's a Boolean, its default is null, but it doesn't matter. So I'm actually self-documenting that in my code, and then string in use. Forget about the loop. Forget about writing all that code and doing your debugging on boundary points. Is the string in use? Well, I take that string, I go to that location in my array, and I ask, does it exist? If the element in the array exists, cool, I'm done. If not, it returns false, also done. Notice, as my collection gets larger and larger and larger, my algorithm doesn't change, it's data neutral. So, there are many, many things I can teach you and we can talk about in terms of collections. But the main thing that I wanted to point out here is an anti-pattern in your code that you should be looking for. And if you run into it, it's a great indicator of using this really nice nuance in associative arrays, string indexing. Just as when you run your explain plan analysis on your queries, if you see a full table scan and you're not running on Exadata, you would say that's a problem. That could cause severe performance problems, and you'd create an index or talk to your DBAs about the best approach to take. If you see a full collection scan of an array in your PL SQL code, you should ask the question, is the order of the data in the collection significant? If not, should I look at alternative indexing? If so, check out string indexing. And you might greatly simplify your code and also improve performance. All right, let's cruise right along, because if I don't, I'll just run out of time. Let's talk about table functions. I'm going to introduce the idea in general, and then we're going to explore the most important feature of pipeline table functions from the standpoint of performance. I'm hoping that all of you know about and use table functions because they're pretty cool. A table function is a function that you can call in the from clause of a query as if it were a table, hence the name. And oddly enough, that syntax isn't quite right either, but we'll come back and look at the example in a moment. So it's a function you call in the from clause of a query and have it treated as if it were a relational table. So why would you do that? Well, in general, table functions allow you to perform arbitrarily complex transformations of data and then make that data available through a query, just rows and columns. Why would you do that? Well, SQL is an extremely powerful language, and you can do an awful lot with it, especially if you follow the writings of Tom Kite. But it can't do everything, and sometimes the logic that you need to construct the data set is highly procedural with all sorts of special rules and formulas that need to be applied to the code. So I have to write this program to generate my data set, but I want to send it back to, let's say, a Java programmer, a JavaScript developer, and so forth, not as a function or a procedure they need to call and then manage that data, but as a select statement. And that's exactly what table functions do for me. I can hide all the complexity behind that function interface and then surface it up as nothing more than a select statement. In addition, the specialized version of table functions called pipeline can have a dramatic impact on performance and also drastically reduce PGA consumption for a fairly specific set of use cases. So table functions have very broad usage. There'll be lots of ways you can apply them. Pipeline table functions are more specific, but when you need them, wow, they are great. So when should you use a table function? So if you want to pass back data sets from the Oracle backend to a non-PL SQL host environment, and they want to deal with rows and columns. In other words, you don't want to have those front-end developers really dealing with the nuances of your data. You want to make it really simple for them. Then you can surface that up with a table function, and often you will then also take advantage of cursor variables. You can improve query performance quite dramatically with pipeline table functions, essentially for parallel query environments. You can also reduce the user perceptions of elapsed time with pipeline table functions. I'll come back to that when we look at that topic. So let's start with a very simple table function example. I want to return a list of names, basically generate a list of names. So sometimes I need 10 names, sometimes I need 100 names. So I'm going to pass in the base name like Stephen, and the number of names I want like Stephen 1, Stephen 2, Stephen 3. And I'll generate the array of names. So I've got a previously defined array type. I extend to make room for the number of elements I need. I populate the elements into that collection, and I return it. And once I do that, once I've created the function that returns my nested table, I can execute it in SQL as follows. I can select column value, and that's the hard-coded name of the column from a nested table or table function that has a nested table of scalars. So if I'm just returning, say, a table of strings or a table of dates, the name of the column is always column value, but you can change it to whatever you want. If I'm passing back a nested table of object types, which we'll look at in a moment, then you have actually the names of the attributes of the object type in the select list. But then what I do is use the table operator. So the table operator says, take this collection, which happens to be returned by a function, but you could also have a collection inside the table operator. Take that collection and turn it into a relational table format. So it does the conversion for us. And then inside the parentheses, I can put a nested table or a V-array, or in 12.1, an associative array, or I can put in a function that returns the same. So inside the call to that table, I pass in my parameter values, and magically it comes back with a set of data. And at this point, I've got a select statement just like any select statement. So I can join, I can union, all of that stuff. Let's take a look. So there's that lots of names function. I can call select value from table, and there's my function call. I can give it an alias if I want to. I can join with other tables. I can do unions. It's just a set of data inside a select statement. You can even put them inside a view, and then all of that information is hidden away. Here's an example of using cursor variables. So a lot of front-end languages like Java can easily fetch back a cursor variable or retrieve a cursor variable and fetch from it. So I can have my select from table, my table function, and then open that cursor variable for that select statement, and then return the cursor variable. And then the Java front end can fetch from that cursor variable, and they have no idea that they've actually executed a function that's doing this complex construction of the data set. So that's the general idea behind table functions. Now, a very common application for table functions is called a streaming table function, and this usually is inside a data warehouse context. So in the example that I'm showing you here, what I want to do is take data from one table, the ticker table, and do a 2-for-1 or a 1-for-2 transformation. One row in ticker goes to 2 rows in the stock table, and then pass back the data to the stock table. Now, the details of it really don't matter at this point, but the basic idea is similar to what I showed you before. I pass in some data, in this case a cursor variable, which is a set of data. I return a nested table. Inside my function, I construct and fill that nested table. And the details of it really don't matter. It's all application specific. But you'll probably want to do a fetch bulk collect when you're getting data from your cursor variable to improve performance. I do my transformations, populating my collection, and then I return my collection. Very cool. Let's take a look. Here's an example of a double transformation. It's called a streaming table function because you stream the transformations along in a single SQL statement. So I'm going to take the contents of the stock table, not as dynamic SQL, but as static SQL. I'm going to say, give me everything from the stock table. And I'm going to pass it to a function as a parameter, an argument. Well, how do you do that? Well, I'm going to put the select statement inside the cursor expression. And the cursor expression basically says, take that data set and turn it into a cursor variable. I pass the cursor variable into my function. It does all the transformations, and it returns a nested table. The table operator takes that nested table, converts it into a relational table format. I'm going to select everything from that. I'm going to put it inside a cursor variable, pass it to another transformative function. It does whatever it's supposed to do. It passes back a nested table, convert it to a relational table format, and then insert it into a new table by selecting all those transformed rows. Wow. Now, you may never get to do anything quite that complicated, but hopefully your eyes are open to the amazing possibilities here. The idea that you can pass a select statement, a data set, to a PL SQL function via a cursor variable, that's pretty cool. The idea that you can take that nested table that you're returning and convert it into a relational table format and then integrate it with your select statements, your database data, is really cool. In other words, you can have data from your session, program-only data that's not in a table anywhere, and you can still manipulate it with and join it with database-based information sitting in relational tables. Nice stuff. Now, pipeline, from the standpoint of performance, pipeline table functions take it a step further. Now, with regular table functions, You can define them this way. You can use them inside SQL, but you could also call this function outside of an SQL statement. However, with pipeline table functions, in other words, as soon as you put the keyword pipeline on your function, this function can only be used inside an SQL statement. So what is this all about? Well, pipeline table functions do something that's pretty much unique in the PL SQL world. They return data iteratively, asynchronous to termination of the function. So in general, when you call a PL SQL function or procedure, or something in your session does, the session stops, it's blocked, until that function or procedure finishes and returns control back to the calling block or the calling SQL statement or the front end. So it sits and waits. Now, that's good for a lot of situations, but it's terrible, for example, when I want to run a parallel query, and my parallel query has a call to a user-defined function, a table function. Because even though the rest of the query can be partitioned and parallelized, the PL SQL function cannot. But a pipeline table function can be called inside a parallel query and be fully parallelized, not parallelized, but run in parallel. And to do that, it has to be able to send the data back while the function is still running. So that's the really unique thing about pipeline table functions. And again, only called within SQL. Why would you use this? Well, as I mentioned, the main application for pipeline table functions is when you execute functions in parallel. So when I've got a select statement that has that's executing in parallel, you've got the parallel query engine, and you need to call a table function. If you want to make sure that it does run in parallel, then you need to add the pipeline syntax, and also add a parallel enable clause to the function that basically tells it how to partition the data set that's coming into the function. Now, another way that you might look at applying the pipeline table function is to improve the speed of delivery of data to web pages, essentially trick the user into thinking that your query is running faster than it is. So I'm on a website, and I type in some criteria, I press submit, and I don't realize it, but I just asked for 100,000 rows of data. So the engine goes out, it executes the query, it starts bringing back the data, and the page just gets bigger and bigger and bigger, and I'm sitting there waiting until it's done. Well, users hate to wait. So what you can do with a pipeline table function is design the back-end query and the front-end code so that it's kicking the data back out to the front end as it's getting the rows out, and the front end can display like the first 100 rows instantly, and even though the query is still executing and retrieving the data back. Now, I have to admit, I have not written that code myself. I'm not a front-end developer except in Apex, and I don't think this will work in Application Express, but I know that others have done so with Java, for example. And finally, the pipeline table functions are a great way to reduce program global area consumption. So memory consumption of arrays, if I've got a regular table function and I build a collection with 100,000 rows of data, it can consume an awful lot of memory. And simply by converting to pipeline table functions, I can drastically reduce the number of rows consumed, or the amount of memory consumed. So what are pipeline table functions all about? Well, they're very different looking from the usual functions in PL SQL. First of all, you add the keyword pipeline to the top. And as I mentioned before, you might also add parallel enable if you want to run it in parallel. And then we're still returning a nested table, usually a nested table of object types. So I have to populate that nested table, right, and return it. No. In fact, I'm not going to populate a local nested table and return it. Instead, what I'm going to do is construct the individual elements that are supposed to go into the nested table with whatever logic you have to follow. And then I'm going to call the pipe row command. And the pipe row command says pipe it back out to the calling query. And then when you're all done, return nothing but control. Isn't that a weird thing to see inside a function? You can actually see return semicolon in procedures. If you want to write some really hard to manage unstructured code, just return anywhere you want. You don't want to do that. But in a pipeline table function, it's the only thing to do because we've already returned all the data. And all that's left to return is control. Let's take a look at some code. So without going into all the details, here's a non-pipeline stock pivot function that takes the data set in, here's the cursor variable, and then does its transformation of 1 to 2. Here's the first one for open, here's the second one for closed, and then it returns that nested table. And here's the pipeline version. So define it as pipelined, construct my open and close object types, but then pipe them back. Don't populate a local nested table and then return control. That's why you get a reduction in PGA. You're not populating a local nested table. Now, in terms of performance, I don't have a parallel query engine I can show you, and in fact, you don't need it to see that it really is different, and I strongly encourage you to run this test. What I've done instead was take my initial transformation, take everything from the stock table, convert it to a cursor variable, pivot from 1 to 2 rows, and then insert into ticker table. So that's my transformation. I've added where row num is less than 10. So I'm doing it for my pipeline version and my non-pipeline version. I only want the first 9 rows. Now, what I was actually doing was transforming 100,000 to 200,000 rows. So let's see what I got performance-wise. So let's take a look at 10G. Pipelining. If I had my pipelining turned on, the first 9 rows were retrieved in 0.9 seconds. Without pipelining, the first 9 rows were retrieved in 3.9 seconds. And back in 9i, look at that, it was 100 times slower. So one of the things you see here is that as Oracle versions increase, 10, 11, and 12, generally speaking, the slower stuff gets faster, and the stuff that was already super fast doesn't improve as much. So there's much less of a difference in performance, but it's still much faster. And what's clearly going on here is that with the pipeline version, every time I piped a row back, the outer query was keeping track of the number. And as soon as it got 9 rows back, it stopped. But with the non-pipeline version, it called the function, and then it waited. And the function took 100,000 rows from stock table, created 200,000 rows for ticker table, passed them back to the nested table, and then the outer query said, thanks, but I just needed the first 9, and threw away everything else. So there was a lot of wasted work in that context. So the point here is that, in general, the pipeline table function really does work differently. It has a clearly significantly different performance profile, as you can see. And the main question will be, do you need it? Can you apply it? One final point about table functions. Come back. Is that you should only pipeline it if you need pipelining. What I have often found when I go out and give talks or get questions from developers is that they conflate the two things together. In other words, they think that every table function should be a pipeline table function. And they add the pipeline logic to it, and they put in the pipe row, etc. There are 2 problems with doing this. One is that if you put the pipeline syntax on it, you cannot use this function outside of SQL. Maybe you don't care, but in any case, it's a constraint that you may not really need to apply. The second problem is that in general, a pipeline function will run a little bit slower than the non-pipeline version when you don't need pipelining. In other words, you're not really using the data asynchronously, you're just calling the function, returning the data. So if you're not running a parallel query, if you don't need to reduce PGA consumption, etc., then adding the pipelining will actually cause a slight degradation in performance. Not very much, but some. So the thing to remember is that table functions serve a tremendous role. So table functions offer this incredible flexibility for PL SQL developers. In other words, you can just bury all the complex logic of constructing these data sets inside your function and expose it as nothing more than a select statement. You can parallel execute your table functions. You can reduce that consumption, all good stuff. But don't pipeline it unless you really need those additional features. Using a table function all by itself is often more than enough. Finally, you can also provide statistics to the cost-based optimizer to help it determine how to come up with the best optimized plan when you have table functions executed inside your SQL statement. So in general, if you're saying select from table X, comma table Y, comma function call, the cost-based optimizer can look at table X and Y and determine a lot about how to optimize the query. But it can't look inside your function and sort out what to do. So you have to give it some information to help it do that. Cruising right along, about 15 minutes left to go. The NOCOPY hint. So this is another very small feature of PL SQL, or at least it involves minimal impact on your code, but can introduce some significant performance improvements. And to understand NOCOPY hint, you have to understand how Oracle passes in arguments or arguments to procedures. And there are 2 basic approaches that you can take, passing by value or passing by reference. When you pass by reference, which is always the case when you pass an in parameter, then inside your procedure or function, Oracle directly references the argument's value that was passed in. Well, that makes sense. But if you pass in, out, or out arguments by a value, then by default, they're passed by value and not by reference. And what that means is that inside your procedure or function, Oracle does not directly reference your actual variable that you passed in. Instead, it makes a local copy of your variable. It makes changes to that local copy. And then if no error is raised, if the program completes without an unhandled exception, then it takes that local copy and it replaces your local variable with that new version. So there's a copy in and a copy out. And the basic reason is that they figure if something goes wrong and there's been an exception, you don't want to have modified your data structure. But you've got the cost of copy in and copy out. So what NOCOPY does is essentially turn off that copy process. You're basically asking Oracle to stop doing that. Don't do a copy in, don't do a copy out. And you'll see a performance improvement. But the key thing to remember is that if you do this, if you add the NOCOPY hint, then Oracle will not automatically roll back or reverse changes made to your variable. So you can end up with data structures that are partially modified. Let's take a look. Okay, so here I've got a package that has two different procedures, pass by value, pass by reference. In my pass by value, notice I have no NOCOPY hint, but I've added the NOCOPY hint into my pass by ref procedure. And that's all you have to do, just that one word. Now it's called a hint or a suggestion because there are a number of circumstances under which Oracle, the compiler, will reject your request. It will not honor it, and it will still do a copy. And you can check the documentation for those situations. But the basic idea is that if you have NOCOPY, then inside your program, when you modify that data structure, so there's my list of numbers, when you modify the data structure, it will actually not be modifying the thing I'm passing in. For example, here's my actual variable that I'm passing in to pass by reference. It will not modify this thing. It will modify the local copy, and only afterwards, when you pass by reference, it will modify that local thing directly if you don't make the copy. And so when you run this kind of code, let's take a look. Let's run it out. Did I turn on my DBMS output? I did not. I'm so bad. Let's do it again. Here's what you're going to see. Here's the difference in behavior to be aware of with NOCOPY. So when I pass by value without the NOCOPY hint, I made a bunch of changes, and it didn't raise an exception, so it doubled all the values. But in my next run, I forced a raise of an exception partway through. And notice before and after, they're all the same. In other words, all the changes were rolled back. But if I added NOCOPY, and I allow the program to fail, or for some reason it does fail part way, notice what happened. My data structure is partway changed and partway the same. So that's the thing to watch out for. Now, in most cases, the argument from, for example, Bryn Llewellyn, the PL SQL product managers, don't worry about that. You shouldn't be concerned about, why didn't you find the file? Because I'm not in the right directory. You shouldn't worry about the fact that the data structure was partially changed because you had an unhandled exception from your program. Something went badly wrong, you're going to stop, you're going to log the error, and propagate the exception out. So I'd say I agree with him. In most cases, you're not going to worry about the fact that your data structure could be partially changed, but you definitely want to be aware of it. Now, I wrote a script, the NOCOPY2 script, which will compare performance with and without NOCOPY. And here's what I saw. Back on 10G, the performance went down from 20 seconds to 12 seconds. On 11.2, from 11 seconds to 8, roughly the same thing in 12. So we're not talking about an order of magnitude improvement. And you probably won't see much of a difference unless you're doing lots of iterations. But clearly, it is a noticeable difference. And it's a nice difference considering that the only thing you have to do is add the NOCOPY hint, the keyword, in both places. That's pretty nice. So keep it in mind. Probably a good general rule of thumb that you can apply in your organization is that every out and in-out argument should be made NOCOPY. There'll be certain circumstances where you might not be able to apply that rule, but in general, that's going to hold. And of course, unless you're talking about an array structure or a large complex structure like a record or an object type, you will almost certainly never see an impact from NOCOPY. If it's a single string, it's unlikely that you'd see an impact. But certainly for any collection of noticeable size, NOCOPY could be a nice optimizer. Okay, optimizing data types. So all data types are not created equal. And there are certain things you should be aware of in terms of different data types that will help you under highly specialized circumstances. For example, the most common one is that if you're doing intensive integer computations, millions of computations, you should avoid integer and instead use PLS integer or binary integer, which is its equivalent, subtype cousin, to do your integer computations. And as long as the integer values fall within the PLS integer range, essentially 2 to the 31st minus 1 to minus 2 to the 31st plus 1, about 2.14 billion. As long as your numbers are in that range, you can use PLS integer, and it'll be significantly faster if you have lots and lots of computations. But for most normal integer operations, it really won't matter. The only reason then to use PLS integer is that it just looks like you know what you're talking about, and that's always kind of nice, even if you don't really need or will see the impact of that data type. In addition, if you're working with floating point values, Oracle does offer specific data types for that, binary double, binary float, and you could see significant improvements there. But again, for most situations, the impact will not be noticeable. And there's another data type I should mention here. It's called simple integer that was added in 11G. And if you're doing native compilation, if you're compiling your code down to machine code, which is what is now supported in 11 and higher, then you can use simple integer, and you can see some improvements in performance over PLS integer. But there are some differences in semantics and overflow and so on and so forth. So there are some things to be aware of. Again, these are the kind of items that you should not worry about up front. But if you identify a bottleneck in a procedure, and it's running too slowly, and you look inside and you're saying, oh my gosh, we're doing 25 million integer computations, and I'm using integer, then you could look at making those kinds of very highly specialized changes, and you could see a change, see an impact. So some ideas for optimizing SQL and PL SQL: the returning clause, implicit versus explicit, and dynamic SQL. And I think I took the DBMS parallel execute out. So let me just talk about that. There's an 11G package, DBMS parallel execute, that you can actually ask it to execute DML statements. So if you're doing lots of updates, lots of inserts, etc., you can actually use DBMS parallel execute to set them up to run in parallel, to partition the rows that are being worked on and then executed simultaneously. You need DBA privileges, or you need the DBA to give you privileges on this package to use it. But it can be enormously helpful for large batch processing. The returning clause, this is added back in Oracle 8, and the basic idea is that if you're modifying data in a table and you need to get information about the rows you just modified, rather than execute a separate select statement and an additional context switch against the database, you can simply add the returning clause to get the information back right away. The most obvious application of this is if I'm doing an insert into a table that generates the primary key with a sequence and a trigger, and I need that primary key right away. Rather than selecting again after the insert, I just put it all together with a returning clause. My apologies, I'm a terrible typer. Terrible typer. So here I have an insert followed by a select. Here's a much better way to do it. Do an insert into the table, and then return the values directly, right away. And you can see some significant improvements in performance, assuming, again, you're doing this for a lot of rows of data. Hopefully you all know about that. It's been around a long time. And remember, if you're modifying multiple rows of data, so if I'm doing an update that might span 100 rows, you need to combine the returning clause with bulk collect. So return bulk collect into an array of those values. Implicit or explicit, which is faster? Ah, yes, the age-old question that should no longer be a question. This is a great example of how you always have to verify what the gurus say, what the great minds say. So, people tend to listen to myself or Tom Kite, and whatever we say, they go and do. The problem with that is that we change our minds over time because the technology changes or we learn new stuff. And so you might be stuck on an old version of us. So back in version 1 or edition 1 of my book, PL SQL Programming, back in '95, at that point, an explicit cursor fetching a single row was faster than an implicit cursor. But shortly thereafter, as of Oracle 7, that was no longer the case. And for years, this advice has lingered, and it's like a full story that you have to check against Snopes.com about. Today, the thing to remember is that if you're fetching a single row of data, an implicit select into will almost always be faster, maybe 20% faster than an explicit. So for single row selects, you should always use an implicit. And you can check, if you look at the single row fetch script, you can actually look at 4 or 5 different ways of doing a single row fetch and compare them. I won't take a look at that now. Use a select into, but really the more important piece of advice that I could give you is that whatever approach you take to fetching that row or even fetching multiple rows, hide the query behind a function. Call the function and then use the data returned by the function. You're hiding the implementation of the query behind a function interface. Why? Well, among other things, because then if in Oracle 13 we discover that, oh my gosh, for some reason, intentionally, unintentionally, explicit fetches are now faster, a lot faster than implicit select intos, you can just go inside your function, make the change in that one place, and you're done. As opposed to writing a memo out to everybody in your team saying, you know what, I told everybody explicits are not as fast as implicits, but now that we're on 13, they're faster again, so please change your implementation. No. Hide the query, make sure it's written just once, put it inside a function, and then if you have to change it for whatever reason, you can change it in just one place. My favorite rule, single point of definition. Optimizing dynamic SQL, there are a couple things to be aware of. First of all, hopefully you all know this, use native dynamic SQL, execute immediate instead of DBMS SQL. DBMS SQL has been around since Oracle 7, and it is a very powerful package, but it's very complicated, and it's relatively slow compared to execute immediate, which was introduced in Oracle 8. So in general, for almost every dynamic SQL situation, you should use execute immediate. DBMS SQL is essentially reserved for the most complex outlier requirements for dynamic SQL. On a more routine basis, the most important thing from a performance standpoint is bind rather than concatenate whenever possible. Let's take a look. Let's look at the 10G version. So I'm passing in a column name, the start and the end dates, and the value. And I want to update whatever column I've specified with the value that's specified for everybody who's hired between these two dates. And I thought I'd show you the 10G version because this uses another new feature in PL SQL, which is the Q qualifier. If you've got one of those situations with dynamic SQL where you have a lot of duplicated or repetitive single quotes because you have to resolve like 3 single quotes into 1 or 5 into 2 or whatever crazy stuff you're doing, you can use Q to specify alternative delimiters for your string. And then inside these delimiters, I can use a single quote without having to have doubles. So just in case you haven't run into that before, that's what the Q is about. So here's an example of using concatenation. I'm constructing my update statement on the fly each time. I'm concatenating the different chunks of logic, and then I'm concatenating in the values. And notice it's really cumbersome. There's a lot of code. I have to take my date, convert it to a string, and so on and so forth. So there are 2 main problems with this approach. One is that the code is awfully complicated, hard to read. The second is that every time I have a different value for start and end and val, I end up with a different physical SQL statement resulting in excessive parsing. So use binding instead. Here's the same program with binding. So update employee, set the column equal to the value. So whenever you see a colon, that's the placeholder. And then I've got my bind variables that I bind in my using clause. So the SQL statement that's parsed is kept separate from the values themselves. And then if I change my values, the SQL statement is physically exactly the same, which means Oracle can avoid additional hard parsing. Notice you cannot have a bind of the column name. In other words, I can't do this. You can't bind in elements of the SQL statement itself. In other words, Oracle can't parse the statement. It can't know that this is valid unless it knows the name of the column. So that has to be concatenated in. But you don't have to worry about performance, and you don't have to worry about potential SQL injection for this kind of concatenation. It's concatenating a chunk of the syntax itself. I should take that back. You still could have problems with SQL injection with any kind of concatenation. So you have to watch out for that. But definitely bind whenever possible, and binding by itself will reduce the chances of a SQL injection problem anyway. Now, I've got a few minutes left, and usually I would say, oh, this is great. I finished early. I've got time for questions, which I will still have. But I realized that I left out a slide about executing functions from SQL more efficiently. So I'm going to finish up with that, because especially it brings in some new features from 12c. So let's do that one last point, and then I'll take questions. Now, as I'm sure you know, when I execute a select statement, I can call my own functions, a user-defined function inside that select statement. And that is really handy. I essentially can extend the SQL language. But there are a number of different ways that we pay a price when we're doing that. The most important is a context switch. So even though SQL and PL SQL are tightly integrated, they have different virtual machines, different engines running the statements. So for example, if I have a PL SQL block, and inside that block I call a select statement, then there's essentially a transfer or a switch from the PL SQL engine to the SQL engine to execute that select statement. If then inside that select statement I have a function, then the SQL engine has to switch back to my function for the PL SQL engine to execute the function. And if my function has a select statement inside of it, you get the idea. We can be bouncing back and forth with recursive, nested context switches, which can be quite expensive. In fact, that is the reason that bulk processing is so fast, because it reduces the number of context switches. But we still want to be able to do this. So there are a number of aspects around user-defined functions. One is that they probably shouldn't have any SQL inside of them. If you want to call them inside SQL, they should be clean, deterministic functions without any side effects. But in addition, we want to look for ways to improve the performance. And the best way to do that, and available in 12c, is that, let's go back to my function. There we go. I can add a pragma. So there's a new pragma. A pragma is a compiler directive, a command to the compiler. And I'm telling it, I'm going to use this function almost all the time, or maybe exclusively, as a user-defined function. And when I do that at the time of compilation, then Oracle will optimize basically the way that the function is set up, so that when the SQL engine calls the PL SQL engine to call this function, the context switch cost is reduced. There's still a context switch, but it's much lower than it was before. So that's a key optimization to look for in Oracle 12. You can greatly reduce the context switch cost simply by adding the pragma. There's another feature which is called the with clause. You can have a with function. This is pretty cool. I can define a function inside my SQL statement. This will also reduce the context switch cost somewhat, but the UDF pragma is actually better. So if all you're looking for is a way to reduce the cost of calling this function inside SQL, keep it as a separate function in PL SQL and add the UDF pragma. The with function clause is really primarily helpful when you have the same simple formulas that are being executed repeatedly in the same SQL statement. You just want to avoid repeating it. So you want to define it in one place. So both of these are helpful. The UDF pragma is the far better of the two in terms of simplicity and impact on your code. And if any of you are looking at this code and wondering what the heck it is, these $ indicate that this is conditional compilation. And this means that at the time of compilation, the PL SQL compiler will ask for the value of include UDF. And if it's true, it will include the pragma. Here, for example, I'm setting the flag, the conditional compilation flag, to true, and then recompiling the function, and that will add the pragma into it. Check out conditional compilation if you want to explore that in more detail. So now I will conclude. So first of all, in terms of optimization, the most important thing is to write SQL, not PL SQL as much as possible, and tune your SQL first. When you go to your DBA to say, hey, can you please add 15 indexes, I need to make this application run faster, and your DBA says, go tune your code first, please do not be offended. We all know there's more we could do, and the primary place to start is SQL. Then, as you're writing your code, always proactively apply the key optimization features. Definitely, bulk collect and FORALL. Look for all those loops that have DML inside them. Updates, inserts, and deletes in a loop are the key anti-pattern. In-out arguments that pass collections, add NOCOPY. Look for functions you can apply the result cache keyword to, and the returning clause is also a nice, quick, and easy win. Beyond that, prioritize maintainability over obsessive optimization. Remember, your code will live on for years and years and years. You want to make sure that people working with your code 5 years from now don't have a nervous breakdown when they need to fix a bug or try to make it run faster. But identify those bottlenecks using DBMS HProf or DBMS Profiler, and then apply the more specialized optimization techniques as needed. For example, changing the data types. You're almost never going to see an impact from that unless you've got a fairly extreme circumstance. Confirm that you're always doing binding and not concatenating and so on. And then so you'll do those final, much more optimized tweaks to your code, like setting your inlining, turning on your inlining in a specific program. So, thanks very much for attending. I've now used up my hour quite fully. What I'd like to do is switch over to see if we have any questions that I'll take via chat, and then we'll be finished for the day. And I didn't invite you to do this before, so I guess right now, if you'd like, you can, whoops, come back. You can chat. You can type your question into the box, and I will answer it. Sorry, every time I click into that window, it goes away. So do we have any questions? Chat. There we go. There are questions. I was looking in the wrong place. Okay. So does a for-reckon cursor, where cursor 1 is a declared cursor, get automatically optimized into bulk operations as a for record in select? So the question is, if I have, let's go to, the question was, well, I think you can see it right here. Either if I have a cursor or a select inside parentheses, the optimization is the same thing. So it doesn't matter which approach you take. If you're writing a cursor for loop, it will be optimized. Yep. There's a question here about, I missed part of the webinar. Is it possible for me to view the recorded version? Yes, this is being recorded, and ODTUG will post it on their YouTube channel, and we will make sure everybody knows about it. Of course, follow me on my SF on PL SQL blog or Twitter feed, and I'll let you know about it there. Holy guacamole, such an enormous amount of tips, of ideas. Processing will take a while. It's true. So there's no question that with the flurry of information I've thrown at you, you can't possibly have internalized all of this. You'll have the recording to watch later on, and certainly you've got a lot of access to resources online to help you deepen your knowledge about any of these areas. Do table functions also cause a context switch? Yes. Anytime you call a PL SQL function inside an SQL statement, you will have a context switch. And then the question becomes, how do you reduce the number of calls to the function, and or how do you reduce the cost of calling that function? So with the Pragma UDF, let's get over there, you can use the Pragma to reduce the cost of the context switch. But then you also look for ways to reduce the number of times you're calling the function. And the main thing to think about there is that whenever you see a user-defined function inside the where clause, alarm bells should go off, because this function is being called for every row that's being evaluated. Calling a function inside the select statement still has a transfer, a context switch, but it's only going to be called for those rows that have been filtered out by the where clause. So this is the worst case scenario, and you may still want to do it, but be aware that it's going to be executed a lot. This is the second worst to be aware of, because it'll only be called for the rows that are selected. And then if I call it inside a table operator, you're still getting a context switch, but there it's just once. You're only calling the function once. So I don't think you have to worry too much about the impact of the context switch there. And I have a question here. Can you give us, again, the address of the example code? You bet. So all you have to do, I'm just going to type it in at the top here, is go to oracle.com/OLL for Oracle Learning Library, and then /PLSQL to get to the PL SQL Learning Library. And if you're not familiar with Oracle Learning Library, there are just hundreds and hundreds and hundreds of resources available there, most of them videos, tutorials, Oracle by examples, that will help you learn about all sorts of different Oracle technology areas. I have a couple more questions, and I think we're going to have to call it to a halt. Does a pipeline table function also do a context switch between SQL and PL SQL for each row returned by the pipe row? That's a good question. I've gotten that question before, and the answer I need to give you is don't worry about it. Some of the internals of the PL SQL engine and communication between the engines are changed with each version, and we encourage you to not get too caught up in internal details. So when we get a question like, does a pipeline table function also do a context switch for each row returned by pipe row? My question back to you would be, does it matter? Because either you need a pipeline table function or you don't. If you need a pipeline table function, if you have to execute that table function with a synchronous returning of data, then it's going to help you no matter what's happening with the context switch. So at that level of detail, the requirements of your code are driving what you're going to do, and whether or not there's a context switch going on is pretty much irrelevant. Final question. Does an associative array improve collections, union, or distinct functions via nested table versus a nested table? I must admit I'm not exactly sure of that question. I think what's being asked is that when I'm using nested tables, I can take advantage of multi-set operators, which is another really cool feature. Let's get over to that. Let's see, 10G mult. So, darn, here we go. How's that? Yeah, here we go. So when I'm working with nested tables, I can use multi-set union, multi-set intersect, multi-set distinct, multi-set intersect to actually perform high-level set operations on my nested tables. You cannot do these kinds of operations with collections. So I believe the question is, if I'm working with associative arrays and I write my own logic to do unions and intersects and minuses, minuses or accepts, will that be faster than using these high-level operators? And my answer is probably not. There may be some situations where it would be faster because manipulating associative arrays in PGA are really fast. But I would say generally if you want to do high-level set operations on your array structures, use nested tables and use the multi-set operators, partly because then as Oracle optimizes those features over time, you get to take advantage of those optimizations. If you write the code yourself, first of all, it's going to be hard, I think, to get it right. And second of all, over time, it might get significantly slower than the multi-set option. Okay, I think I've overstayed my welcome with some of you. You seem to need to have to go back to work. So let's do that. Thanks again for joining me for this final webcast on PLSQL for the year. We'll be obviously getting back to webcasting in the new year. I hope you found this enjoyable, and certainly check out all the resources at the PL SQL Learning Library. Thanks very much. Happy coding and Happy New Year.